Hello, everyone, and welcome to this training presentation on the methodology for strength analysis of dynamic subsea lines in OrcaFlex. My name is Mehdi. In this presentation, I will introduce a structured global to local strength analysis methodology applicable to dynamic umbilicals, flexible pipes, and steel catenary risers. The methodology covers load case definition, global to local response assessment, identification of governing design loads, and final design acceptance. With this introduction, let's begin. This is the agenda for the presentation. I will begin with the purpose and main objectives of Stearns analysis. I will then review the principal design inputs and the critical structural checks. After that, I will explain the acceptance criteria and bring all elements together in the overall strengths analysis and load case metrics methodology. I will then discuss how strengths results influence the global configuration and ancillary components. Finally, I will move to the practical implementation and show how the structural load cases can be generated automatically in OrcaFlex using an Excel spreadsheet and a model variation template. This section introduces the main objectives of Stearns analysis. Before discussing load cases and OrcaFlex settings, it is important to understand what the analysis must demonstrate and what engineering decisions are expected from the results. This slide summarizes the six main objectives of Stearns analysis. First, Stearns analysis confirms the structural integrity of the system under the governing environmental, operational, installation, abnormal, and damaged loading conditions. Second, it identifies the governing load cases and the critical locations along the risers, umbilical, or flexible pipe. Third, it provides reliable design loads for local components and interfaces. Fourth, it demonstrates compliance with the applicable project code or supplier acceptance criteria. Fifth, it supports configuration development and optimization when the initial design doesn't satisfy the required criteria. And sixth, it assesses touchdown zone and seabed behavior where the system interacts with the seabed. These six objectives are closely connected and together form the basis of the overall strengths assessment. In the following slides, I will discuss each of these six objectives uh, individually and explain its role in the design process. Stearns analysis checks whether the system can withstand the governing combinations of environmental, operational, pressure, temperature, installation, and damage condition loads. The loading may include waves, currents, vessel motions, vessel offsets, internal and external pressure, line contents, and transient operations. The calculated response must remain within the allowable limits for the applicable limit states, such as SLS, ULS, and ALS. For dynamic systems, the governing response often results from the interaction of several load components rather than from a single isolated maximum. A riser, flexible pipe, or umbilical is not equally critical along its full length. The hangoff may govern end force and angle. The sag or hug bend may govern curvature, and the touchdown zone may govern compression, bending, or seabed reaction. Stearns analysis therefore identifies both when the governing response occurs and where it occurs. Typical review location include the top connection, bend stiffener or stress joint, buoyancy section transition, lower catenary, touchdown points, touchdown zone, seabed contact region, clamps, tethers, and end fittings. A key output from the global analysis is a reliable set of interface loads for local design. These loads may be required for bend stiffeners, bend restrictors, hang-off structures, tapered stress joints, I-tube, J-tube, clamps, connectors, tethers, holdback devices, anchors, and local finite element models. The load must be traceable to the governing global load case and should normally be provided as time consistent associated response sets rather than as unrelated independent maxima. Strength analysis is also a formal verification activity. The analysis demonstrates compliance with the project design basis, client specifications, applicable DNV API or ISO requirements, supplier allowable limits, material restrictions, and installation or operating philosophies. The applicable acceptance basis must be defined before the results are reviewed. Otherwise, the analysis produces response values but doesn't produce a defensible design conclusion. Stearns analysis is not only a final verification check, it is also a configuration development tool. If the criteria are not satisfied, the results should indicate what needs to change. Possible changes include line length, hang-off angle, azimuth, route, buoyancy module, buoyancy module size or position, touchdown location, bend stiffener properties, wall thickness, material grade, or the addition of a tether or holdback device. The revised configuration is then reanalyzed until an acceptable and practical design is achieved. For steel catenary risers, lazy wave risers, and other catenary systems, the touchdown zone region can be one of the most critical parts of the design. The assessment should consider touchdown point movement, seabed reaction, local curvature, axial compression, contact length, cyclic sliding tendency, and the adequacy of seabed friction. If the response is not acceptable, mitigation may include a holdback device or tether, route adjustment, buoyancy modification, or a more detailed pipe soil interaction model. Touchdown zone conclusion should be aligned with both strength and fatigue requirements. I will now move to the main inputs required for strength analysis. A technically correct load case matrix depends on complete and consistent input data, the global model, environmental data, vessel data, line state, boundary conditions, and acceptance limits must all represent the same design condition. The main input groups are summarized here. They include the design basis, line and system properties, global configuration, boundary conditions, vessel or floater data, and environmental inputs. These categories are closely linked. For example, the vessel offset must correspond to the selected environment and mooring state, while the pressure, temperature, contents, and component properties must correspond to the selected operating condition. In the following slides, we will examine each of these input categories in more detail, beginning with the design basis and analysis criteria. The first and most important group of inputs is the design basis. The design basis establishes the governing requirements for the complete strength assessment. Without a clearly defined design basis, OrcaFlex can calculate the structural response, but we can determine whether the correct conditions have been analyzed or how the results should be evaluated. The first input is the design life. This defines the period for which the system must remain fit for service and establishes the basis for life cycle conditions such as start of life, end of life, corrosion allowance, marine growth, and buoyancy degradation. The next input is the set of applicable codes, standards, client specification, and project requirement. This document defines the design philosophy, required load combinations, limit states, safety factors, and verification requirements. The design basis must then identify the applicable limit states, normally SLS, ULS, and ALS. Each load case must be assigned to the correct limit state because the required design factor and allowable limits may differ. It must also specify the relevant environmental return period for normal operation, extreme events, abnormal conditions, installation, and accidental or survival cases. These return periods are linked to the corresponding waves, current, wind, vessel offset, and system conditions. The applicable load, resistance, and safety factors must also be defined and applied consistently with the governing code and limit state. Care is required to confirm that these factors have not already been included in the supplied met ocean data, vessel offsets, material allowables, or supplier limits. The design basis should also identify the applicable acceptance criteria, although I will discuss these criteria in more detail later in the presentation. And finally, the design basis must clearly define the normal, abnormal, installation, hydro test, damaged, and survival condition. Each condition should be linked to the appropriate environment, vessel or mooring state, pressure, temperature, contents, configuration, and limit states. In practice, I would review and freeze the design basis before finalizing the strength load case metrics. If the design basis changes, the load case metrics and the resulting conclusion may also need to be updated. The key message is that the design basis defines what must be analyzed, which conditions must be included, and how the overall strength assessment will be structured. The line property inputs define the physical and structural behavior of the system in OrcaFlex. These include geometry, wall thickness, coating or shear properties, mass, submerged weight, axial, bending and torsional stiffness, contents density, pressure, temperature, and applicable allowable limits. For a sterilizer, the stress diameters and pressure related properties must support the selected code check. For a flexible pipe or umbilical, the global properties must be consistent with the supplier cross section model, and the local acceptance methodology. The configuration inputs define the overall arrangement of the system. These include the system type, hang-off location and angle, azimuth, route, water depth, line length, buoyancy layout, touchdown position, attachments, and preliminary bend stiffener, bend restrictor, or stress joint properties. These parameters control the static shape and strongly influence tension, curvature, compression, interface loads, and touchdown zone response. Therefore, configuration control and model revision control are essential. Boundary conditions define how the line is connected to the vessel, seabed, or subsea structure. Important inputs include the top and bottom connection types, rotational and transitional stiffness, connection coordinates, local access, no moment direction, and pinned or fixed connection assumption. This is particularly important for bend stiffener design. A pin top connection may be used to obtain preliminary end force and end angle design combinations, while the final selected component should be verified using the final connection and a stiffness representation. The floater is a major dynamic boundary condition for the connected line. The model should use the correct vessel position, heading, draft, offset, motion reference point, RAO origin, phase origin, and RAO set. Where applicable, low frequency motions, prescribed motions, time histories, coupled mooring response, and static list should also be included. The analyst must verify the direction and phase conventions because an incorrect RAO or heading convention can produce apparently reasonable but technically invalid results. The environmental inputs include waves, current, and wind related effects. For wave, the analysis may use regular or irregular waves. Irregular wave inputs normally include significant wave height, wave period, spectrum type, gamma, direction, directional spreading, random seed, number of realizations, and simulation duration. Current inputs should include the complete depth dependent profile, magnitude, direction, associated environmental conditions, and any required shear profile sensitivity. Wind generally acts on the vessel rather than directly on the submerged line, so its main effects are commonly represented through vessel offset, heading, least, mooring conditions, and vessel motion. Care is needed to avoid double counting when wind effects are already included in supplied offset or coupled motion data. The next section presents the critical checks used to assess the calculated response. The governing checks depends on whether the system is an umbilical, flexible pipe, or a steel catenary riser, but the common objective is to identify all relevant failure modes and interface demands. This slide presents the 10 critical checks considered in the Stearns assessment. These, these include maximum and minimum tension, compression, curvature and minimum bend radius, bending, bending moment, stress and strain utilization, combined tension, bending pressure utilization, hang-off and top interface loads, bend stiffener design loads, shear force, and touchdown zone or seabed interaction. The governing checks depends on the system type. Steel catenary risers are commonly assessed using combined stress, buckling, pressure, stress joints, and touchdown zone criteria, while flexible pipe and umbilical are more common governed by tension, compression, curvature, minimum bend radius, component strain, and supplier defined limits. Different checks may also be governed by different cases and location. Therefore, the strength assessment must review the full load case metrics and the complete line rather than relying on the overall governing cases. In the following slides, I will discuss each of these 10 critical checks individually and explain how each contributes to the overall strength assessment. Maximum tension should be checked against the applicable allowable tensile capacity. Depending on the system and criterion, the relevant response may be effective tension, wall tension, or a supplier defined tension measure. Critical location can be include the hang-off, upper catenary, sag or hog bend, lower catenary, touchdown region, connectors, clamps, and bend stiffener root. The governing tension case should also be reviewed with its associated curvature, angle, moment, or local response where required. Minimum tension is equally important because low tension or compression can lead to excessive curvature, instability, local buckling, or undesirable seabed behavior. The, the review should identify whether compression occurs, its magnitude, location, duration, and associated curvature. Compression is commonly important near buoyancy transitions, sag and hog bands, the lower catenary, touchdown zone, and seabed contact region. For flexible pipes and umbilicals, the allowable compression may be controlled by supplier data or component behavior. Curvature and minimum bend radius are fundamental checks for all dynamic line types. The required can be expressed as maximum curvature being less than allowable curvature or minimum bend radius being greater than allowable minimum radius. Critical locations often include the bend stiffener, bend restrictor, sag and hog bands, buoyancy section ends, touchdown region, and installation overboarding zone. The mesh must be sufficiently refined in these areas, and a discretization sensitivity should be performed where local curvature controls the conclusion. For steel risers and other pipe type systems, bending moment is a primary response quantity and contributes directly to combined stress and buckling checks. OrcaFlex can report the total moment and its local components. For flexible pipe and umbilicals, global bending moment may be less useful as a direct acceptance quantity because their layered cross sections require supplier specific stress or strain recovery. In those systems, curvature, minimum bend radius, component strain, and supplier utilization normally provide the more meaningful acceptance basis. For steel risers, the assessments typically includes axial, bending, hoop, and equivalent stress together with strain and combined utilization. Pressure, corrosion allowance, wall thickness tolerance, and material properties must be treated consistently with the selected code. For flexible pipe and umbilicals, direct homogeneous pipe stress results are generally not sufficient. The assessment should use supplier stress factor, component strain limits, cross-section analysis, local finite element analysis, or supplier-defined utilization envelopes. The governing strength condition may result from the combined effect of tension, bending, internal pressure, external pressure, compression, and curvature. Therefore, independent maxima should not be assessed in isolation, where the governing code requires a combined interaction equation. For steel catenary risers, the combination may control equivalent stress, local buckling, collapse, burst, or code utilization. The correct design factors and minimum design wall thickness must be used for relevant operating category and limit state. It should be mentioned that for flexible pipes, combined loading is also important, but the assessment is normally performed using supplier cross-sectional analysis and supplier-defined utilization envelopes because the loads are shared among multiple structural layers. For umbilical, the equivalent assessment is normally based on tension, curvature, interaction, and component level pressure, stress, or strain limits. Therefore, the rigid pipe combined tension bending pressure equation should not be applied directly to the complete umbilical. The hangoff is where the global response is transferred into the vessel or support structure. The required outputs may include top tension, end force and components, end moment, bend moment, shear force, EZ angle, hangoff angle, connector load, and vessel interface reaction. The sign convention, coordinate system, and load direction should be clearly documented. For local design, the interface package should identify the load case, time, operating category, and associated response values. For preliminary bend stiffener design, the top connection is commonly represented as pinned so that the governing and force and angle combinations can be extracted without imposing the final component stiffness. The supplier input set should include maximum EZ angle with associated end force, maximum end force with associated EZ angle, and the associated moment, shear, and top tension. For each operating category, the critical cases should be selected in a structured manner. After the supplier provides the bend stiffener design, the final properties should be incorporated into the global model and verified in the applicable strengths, interference, and fatigue matrices. Shear force should be reviewed at interfaces where transverse loading is transferred into a local component. These locations include the bend stiffener root, hangoff, connectors, clamps, bell mouth, guides, and bend restrictors. At a line end, increasing misalignment between the end force vector and the local axial direction increases the transverse component. Therefore, a large Z angle combined with a large end force can create a significant shear demand even when the axial tension remains acceptable. For steel catenary risers and lazy wave systems, the touchdown region may govern the design. The assessment should include touchdown zone curvature, compression, seabed reaction, contact force, contact length, touchdown point movement, and sliding behavior. Soil friction and stiffness influence both the global shape and the local response, so sensitivity cases may be required. If the resulting demand is unacceptable, the design may need a route change, buoyancy adjustment, tether, holdback device, or more detailed soil modeling. I will now explain how the calculated responses are judged. Acceptance is not based on a single generic limit. It requires global, local, interface, and system specific criteria to be satisfied for the applicable load case and limit state. The acceptance framework is divided into five parts: global response criteria, local and interface criteria, system specific criteria, the formal acceptance rule, and the wider engineering acceptance conditions. This structure helps separate the global OrcaFlex demand from the local or supplier defined resistance. Global acceptance normally includes maximum effective or wall tension, minimum tension and compression, maximum curvature and minimum bend radius, bending moment, stress and strain utilization, displacement, configuration limits, and touchdown zone or seabed response. These quantities should be reviewed along the relevant arc length and for all operating categories. Clearance should only be retained here where it is an explicit configuration or contact-related strength requirement. The general separation between adjacent line belongs mainly to interference assessment. Local acceptance includes the limits for hangoffs, terminations, bend stiffeners, bend restrictors, tapered stress joints, clamps, tethers, connectors, anchors, and riser base structures. The relevant quantities may include end force, EZ angle, shear, moment, tension, curvature, stress, strain, or local FE utilization. These limits may come from the project, equipment supplier, structural contractor, or a dedicated local analysis. The acceptance criteria must reflect the physical construction of the system. Umbilicals are commonly assessed using tension curvature interaction, compression, minimum bend radius, component strain, and termination or bend stiffener limits. Flexible pipes require checks for armor utilization, minimum bend radius, collapse, burst, annulus, and carcass behavior and end fitting capacity. Steel catenary risers require combined tension bending pressure checks, stress and strain limits, buckling and collapse checks, TSG and hangoff criteria, and touchdown zone or seabed verification. The methodology is common, but the failure modes and allowable definitions are system specific. A common reporting format is the utilization ratio, defined as the design demand divided by the design resistance or allowable capacity. In the usual format, the utilization must be less than or equal to 1. However, this should not be treated as a universal equation. Some requirements are expressed as interaction equation, tension curvature envelopes, minimum bend radius limits, component strain limits, or supplier utilization curves. This governing code, project specification, and supplier definition must always take precedence. Numerical compliance alone is not enough. Before accepting the design, the analyst should confirm that the full envelope has been assessed, the governing cases make physical sense, associated values are time consistent, model and numerical issues have been resolved, supplier and interface limits are satisfied, and required sensitivity cases don't reveal another governing condition. All applicable safety factor and design margin must also be applied. Only then can the results support a formal design acceptance statement. The previous sections explain the objectives, inputs, checks, and acceptance criteria. I will now bring those elements together in the complete strengths analysis methodology from the design basis through load case development, OrcaFlex analysis, governing load extraction, iteration, and final acceptance. The methodology starts with the design basis, including codes, client requirements, met ocean data, and supplier criteria. The applicable SLS, ULS, and ALS acceptance bases are then defined, followed by the complete design envelope covering normal, abnormal, installation, hydro test, damaged, and survival conditions. A decision gate confirms whether all relevant conditions have been identified. If not, the basis is refined. Once the design envelope is complete, the load case variable is defined. These include environment, directionality, vessel offsets, line state, and component state. The candidate matrix is generated by combining only physically consistent values. Engineering screening is then used to remove duplicates and justify exclusions without eliminating potentially governing cases. The result is the final Stearns load case matrix. Each final load case is analyzed in OrcaFlex, beginning with static equilibrium and continuing with the required dynamic simulation. The global responses are screened for tension, compression, curvature, minimum bend radius, moment, stress, strain, and touchdown zone or seabed behavior. Governing cases are identified for each response and location. Local and interface loads are then extracted for bend stiffeners, bend restrictors, tapered stress joints, hang-offs, terminations, clamps, tethers, anchors, and the riser base. The governing response sets must include associated values recorded at the same instant. The complete results are compared with the applicable acceptance criteria. If the criteria are not satisfied, the configuration, local component, assumptions, or load case load case basis is reviewed and the affected analyses are repeated. If all criteria are satisfied, the configuration proceeds to design acceptance. The key principle is that this is a global to local iterative engineering workflow, not merely a batch of simulations. The next section explains how the external results affect the actual subsea design. The analysis may change both the global configuration and the selection or capacity of local ancillary components. The influence of Eastern's analysis can be grouped into three areas: the global configuration, local components, and resulting design action. A useful analysis should not only identify a non-compliance, it should also show which part of the design controls the response and which modification is likely to improve the results. Stern's analysis can influence the route, azimuth, hang-off arrangement, total line lengths, suspended geometry, sag and hog bend positions, touchdown location, buoyancy layout, and seabed contact configuration. For example, excessive hang-off load may require optimization of line lengths, hang-off angles, suspended geometry, or buoyancy arrangement. High hog bend curvature may require modification of the buoyancy section length, uplift, or position. The global strength response provides the design loads for bend stiffeners, bend restrictors, tapered stress joints, hang-off structures, terminations, connectors, clamps, tethers, hold-back devices, anchors, and riser-based structures. A local component may require increased capacity, modified stiffness, or a different geometry. Any change to a component that affect global stiffness or boundary conditions must be incorporated back into the OrcaFlex model and verified. The main design actions include optimizing geometry and buoyancy, modifying component stiffness or capacity, revising wall thickness or cross section, introducing seabed or restraint mitigation, and updating the model for reanalysis. The action should address the actual governing mechanisms. For example, increasing wall thickness may improve ester's capacity, but also increase submerged weight and change curvature or tension. Therefore, configuration changes should be assessed at system level. The engineering methodology defines which strength cases are required and why. I will now move to practical implementation and show how the final strength load case metrics can be converted into OrcaFlex model file using an automated workflow. This slide summarizes the automated workflow used to convert the final strength load case metrics into OrcaFlex simulations files. The workflow starts with one fully validated base OrcaFlex model. The base model contains the data that remain constant across the load case metrics, including the global geometry, line properties, boundary conditions, seabed definitions, vessel data, attachments, and common analysis settings. The load case dependent inputs are organized in an Excel spreadsheet. Each row represents one instance load case, while each column represents a variable that changes between cases. These variables may include the environmental condition, wave direction and period, random seed, current profile, vessel offset, pressure, temperature, contents, component states, and simulation duration. A text template or variation file structure then defines where each spreadsheet value is applied in the OrcaFlex model. In simple terms, the Excel spreadsheet defines what changes, while the template defines where each change is applied. The model files are then generated using the OrcaFlex Excel integration or an approved Python workflow. One model is created for each row in the spreadsheet using a consistent naming convention that identifies the load case and its main design conditions. However, automatically generated models should not be acceptable without review. Before launching the complete batch, representative generated models must be opened and checked manually. The review should confirm the wave parameters, current profiles, environmental direction, vessel offset, pressure, temperature, contents, component properties, simulation duration, and results extraction period. It should also confirm that all placeholders have been replaced correctly. This leads to the QA decision shown in the workflow. Do the representative generated models pass the QA checks? If the answer is no, the source of the error must be corrected in the base model. Excel in the base model, Excel matrix or template, and the affected cases must be regenerated. If the answer is yes, the complete approved the complete approved Stearns load case matrix can be proceed to batch simulation. During batch execution, failed, incomplete, or numerically unstable simulation should be identified and reviewed rather than omitted automatically. The simulation status and any rerun decision should remain traceable. The automation process can then be extended to post processing. This may include extracting global maxima and minima, identifying governing load cases and critical locations, collecting associated response values, generating interface load tables, and preparing utilization and acceptance summaries. The key message is that automation improves consistency, traceability, and the efficiency, but it doesn't replace engineering judgment. Generated model must pass the required QA checks before batch execution, and the final result must always be reviewed for physical consistency and engineering validity. This brings us to the end of the presentation. The key message is that the Stearns analysis is a structured global to local process. It starts with a complete design basis and load case metrics, continues through verified static and dynamic OrcaFlex analysis, and finishes with governing and associated response sets, local design inputs, configuration optimization, and a clear integrity conclusion. Thank you for your attention, and I hope this presentation provides a useful framework for Eastern's assessments of umbilical, flexible pipes, and steel catenary riser in OrcaFlex.